Hello, everyone. This is the lecture for section 4.8, L'Hopital's rule. We're going to take a step back toward limits, okay? But we're going to use derivatives like a lot in this section. Even though we're stepping back, this is an application of the derivative, okay? So in this section, we're going to be doing what's called L'Hopital's rule. Basically, there's a bunch of equations and expressions that at the moment we know how to take the limit for, right? And at the very least, very least, right? If we need to find the limit, we can do it numerically. If you guys remember how I made you guys do those tables that go like 4.8, 4.9, 4.99, 4.999, and then from the other end, right? 5.1, 5.01, 5.001. I made you guys get closer to a specific value, right? So at the very least, we can do the numerical version, the one with the table, and we can do it graphically, right? We can just sort of plop it on a graphing calculator, make a graph of it somehow, right? And then just look at it and say, oh, yeah, okay, this looks pretty, it looks like the limit's going to this thing, right? There's a fair amount of equations still that we have no idea how to take the limit of, okay? And one of the most useful tools in order to find those limits is this thing right here, L'Hopital's rule, okay? So first of all, what I want everybody to do, I know this is a little wild, right? But you know, you guys are watching this through video, is within your group, right? Go ahead and find the limits of these functions, okay? Go ahead, do it either numerically, so using by table, or graphically. I'm pretty sure everybody's going to probably be doing this graphically, okay? Find the limits of these equations, okay? And now let me continue on from here. I'm going to put these up at the same time while I'm talking, okay? So all of these limits that you are looking at right here that you guys are going to be doing for a quick check, they have a limit. It is a real number, okay? They all approach some value, okay? But at the moment, we have no mechanism to solve for these, right? I mean, you can try, common denominators. You can try multiplying it by the conjugate. You can try all sorts of voodoo math, right? But it's not going to get you anywhere, okay? But as you guys will find out, that these limits, they do actually exist. They approach a real number, right? So how do we figure these out? So first of all, what I want to do is I want to go into a couple definitions here, okay? So the first definition is we're talking about this h of x, okay? That's an arithmetic combination of f and g. It doesn't matter which one of these you want to talk about, okay? So either f of x divided by g of x, f of x minus g of x, f of x to the g of x, etc. Any combination you want to put, okay? And what we're going to do, excuse me, is we're going to consider this limit right here, the limit as x approaches some value a of f of x, okay? The following forms are considered indeterminate forms, okay, of the solution of this, okay? Let me actually do it in another color here. 0 times infinity, infinity minus infinity, 1 to infinity, infinity to the 0 power, 0 to the 0 power. I'm running out of colors here. 0 divided by 0, and infinity divided by infinity, either the plus or the minus of it, okay? So all of these are considered indeterminate forms, okay? So if you take a look at each one of these indeterminate forms, right, they look a little wild, right? So let me take a couple of them, right? Let me take a couple of them. Let's discuss this one, right? Let's say you had the limit of, this is gonna be probably some multiplication, right? Let's say you had the limit of f of x times g of x, right? And it's equal to 0 times infinity, right? You could argue that, well, it's 0, right? So 0 times anything should be 0, right? But this is the limit of something, so it's approaching 0, right? While the other limit is approaching infinity. So which one's taken out the other one quicker, right? Is the limit as it approaches a equals 0? Is that one the one that's taken over? Or is the limit as x approaches a the one that's taken over? Or the infinity one, is that one that's taken over, right? Same thing here, right? Let's say you had a limit that's infinity minus infinity. Which one of the infinities is bigger, right? Is the limit as x approaches a of f of x, that first infinity, is that one the one that's taken over faster? Or is it the other one? Is it the limit as x approaches a of g of x? That one's also infinity, but it's a minus infinity. So which one's taken over quicker? You guys see the problem here, that these are these are limits that really we don't know. What we're trying to figure out here is which one's taken over faster. Which one is taking over faster, right? Is it the 0 limit that's taken over faster? Is it the infinity limit that's taken over? We have no clue, right? So this is where L'Hopital's rule comes in. So when we look at these problems, and it's just if you take a look at the quick check that's above, right? You'll see that we have this sort of issue, right? So when we do the limit as x approaches infinity of ln of x divided by the square root of x, the one for group 2, right? Both the top and the bottom, right? They are going to infinity. Which one gets there faster? Which one's the one that's going there fastest, right? We have no idea. This is where L'Hopital's rule comes in. So in order to do L'Hopital's, okay, instead of looking at the value of the functions themselves, so instead of looking at each part of, in our case, if we use the notation of the definition, instead of looking at the values of f of x and g of x or h of x, right, we are instead going to look at how quickly the values get there. Okay, whenever we talk about speed in math, right, that means derivative. Okay, so L'Hopital's rule is pretty simple to sort of get a hold of. It's this right here. Okay, so suppose f and g are differentiable functions over an open interval containing x approaches a, except possibly at a, right? Furthermore, assume or suppose that that limit f of x over g of x numerically produces what's called the indeterminate form, one of the ones that is above, right? Then the limit of the function is also going to be the limit of the derivatives. Okay, so basically what we're trying to say here is we are trying to sort of resolve a limit of functions based instead of doing it on the numbers themselves, right? Based on the outputs of f and g, we're looking at the derivatives. We're looking at how fast f and g are growing, and then we're comparing those together. Okay, the answer to that is the answer to the original limit. Okay, so how does this work out, like, for real? Okay, so let's go ahead and go to example 1. Okay, so for this limit, okay, we're going to determine its indeterminate form first and then compute its limit. Okay, so to determine its indeterminate form, we have to figure out which one of these it is, right? Which one of these up here? That one or one of these, right? Okay. So first of all, we're going to go ahead and determine its indeterminate form. Okay. So for this one, all I'm going to do, it's already in a fractional form. So I'm going to do this. I'm going to do the limit as x approaches infinity of e to the 2x minus 1. I'm just going to look at this thing. Okay. If you take a look at this, right, we know that the limit as x approaches infinity, that means we're making our x values infinitely bigger, right? A billion, a gajillion, a zentillion, whatever, right? The x values are getting bigger and bigger. This then goes to infinity. That minus 1's not going to do anything. If e to the x or e to the 2x is there, that's going to blow up to infinity, right? So let's do the bottom now, right? The limit as x approaches infinity of e to the 2x. This is also infinity by the same reason, okay? E to the 2x just keeps growing and growing and growing, okay? So therefore, what we have here is an infinity over infinity. We have the indeterminate form, okay? So keep in mind, L'Hopital's rule says that we can only do L'Hopital's rule if it produces an indeterminate form. So we've proved that we have an indeterminate form here. Got it? Okay. So then I'm going to say f of x is going to be my top, e to the 2x minus 1, and minus 1. Let me make this neater. And g of x is equal to e to the 2x. So therefore, the derivative of this one is going to be 2e to the 2x. Whoops. Let me actually write it out, huh? F prime of x is equal to 2e to the 2x. And g prime of x is equal to 2e to the 2x. Okay? So then now, the limit as x approaches infinity of e to the 2x minus 1 over e to the 2x is equivalent to the derivative, to the limit of its derivatives, right? So it's going to be limit as x approaches infinity of e, whoops, 2e to the 2x. Whoa, 2x divided by 2e to the 2x. And this limit is equal to 1. Okay. That is L'Hopital's rule. So what we have here is this. I'm going to go ahead and use the color coding that's here. This is our original limit, right? We can't compute this using the methods that we learned from chapter 2, right? So instead, we take the derivatives and find the limit of that. And we get this, right? And by doing this, we get it's equal to 1. So now, just to double check our work, let's go ahead and go to Desmos now. Let me make this a little, there we go. E to the 2x minus 1, all divided by e to the 2x. So our original answer, let me do a double screen thing here. Okay. Our original answer from our work says that our limit should be equal to 1. And lo and behold, that's 2. That looks like about 1, right? And look at what happens. It sort of starts to hug that line. So our limit is actually correct. As we go to infinity, the x's start to approach 1. Or the y's, sorry, the y's start to approach 1. Okay, so that's the point behind L'Hopital's rule. Okay, first of all, we have to prove that we had an indeterminate form, right? Then we took the derivatives. The limit of those derivatives get us the limit of the actual limit from the very beginning. Okay, so what I want you guys to do now is now how to use the indeterminate form and L'Hopital's rule. I want you to go back. You found the limits from above. I want you to go back and now look at the actual function, use L'Hopital's, and find the limit. Okay. So what's going to happen in a lot of these, right, is that you are going to have to rewrite them. The easiest way to do it, because this is how L'Hopital's rule is written, is to rewrite them this way. Either 0 divided by 0 or infinity divided by infinity, okay? That's the overall strategy for how to solve these using L'Hopital's rule, okay? The much more difficult ones, these, right, require logarithms to do it. I know this is going to sound weird. I know you guys hate logarithms, but some of these are going to require logarithms to be able to solve them, okay? And the reason why is because of the same reason that we used logarithms when we had to do logarithmic differentiation. I think that was section 3.9, I think, okay? And that reason is that logarithms basically maintain an order, right? So if we know that a is less than, greater than or equal to, right, then the logarithm maintains that order. That's why the logarithm is so useful, okay? And because the logarithm maintains the order, right, we can then use all the logarithm rules that we learned from pre-calc. We can use them here, okay? So here we go. Let's say we needed to take this logarithm right here. Or sorry, let's say we needed to take this limit that's right here, right? I'm going to determine its indeterminate form first, and then compute its limit. Okay, so what I'm going to do is this. I'm going to go ahead and do the limit as x approaches 1 from the positive side of just the minus x minus 1, just the exponent, right? And if you take a look at that, right, if it's approaching 1, right, then what we have here is that this is going to be 0, right? Because eventually this is going to become, let me do it in another color. This is essentially going to become 1 minus 1, which is equal to 0, right? So the limit of just the exponent is 0. Let's go ahead to take the limit as x approaches 1 from the positive of 2x minus 2, right? By the same idea, this is going to be 2 times 1 minus 2. That's what essentially is going to be happening, right? So then this right here is also going to be equal to 0. So we have our indeterminate form. This is equal to 0 to the 0 power. Okay. So that means we have an indeterminate form. We can use L'Hopital's rule with it, right? But we have to get it in that fractional form, that f of x divided by g of x. And that's exactly what we're going to do. We're going to use logarithms in order to do that. Okay, so here we go. So the first thing I'm going to do is just how we did in logarithmic differentiation. I'm going to do y is equal to 2x minus 2 to the minus x minus 1. Okay. This is where I'm going to take the logarithm. So it's going to be the ln of y, right, is equal to the ln of 2 to the x minus 2 to the minus x minus 1. Okay. Here's where we're going to be able to use our logarithm rules. So we have this now. ln of y is equal to negative x minus 1 times the ln of 2x minus 2. That's a times there, right? Okay, we're getting a little closer now. Okay, we still don't have that fractional thing that we need for L'Hopital's rule yet, right? Okay. And the way to do that is we're going to perform a little bit of magic on this thing right here. Okay, and that thing, so ln of y, it's going to be ln of 2x minus 2 all over negative 1 over x minus 1. Okay, so I encourage you to do this to show that, let me erase this really quick. I'm going to do x minus 1 here. I encourage you to do this to show that this expression that's right here, okay, is equivalent to this right here. Okay, it looks very far-fetched, but it's not really if you go ahead and go through the algebra for it. this is equivalent to sort of dividing by its reciprocal. That's basically it, okay? So go ahead, try it out, okay? So now, we're going to be looking at this. So the original idea, right, is we needed to take the limit of this thing. Okay. So this is going to get a little confusing at this point, okay? But I'm going to try to round it out at the end, okay? So what we're going to do here, remember the original idea, the original limit that we're trying to take, try to find the answer to is this, right? Okay. So what we're going to do is we're going to try to find the limit as x approaches 1 from the positives, right, of the ln of y, which is equal to the limit as x approaches 1 from the positives of this thing up above, right? The ln, the ln of 2x minus 2 all over negative 1 over x minus 1, okay? Okay, so notice we're still trying to find the limit here, okay? And I want everybody to take a look at this thing now. Okay. What we have here now is we have something that looks like it's going to do this. Infinity over infinity. So we have yet another indeterminate form, right? Okay. But now we have it in a fractional form that is dictated from L'Hopital's rule. So this is the thing that we're going to be using L'Hopital's rule on. Okay. This is the thing that we're going to be using L'Hopital's rule on. Okay. So I'm going to go ahead and crawl up here. So my f of x, I'm going to say, is my ln of 2x minus 2, and my g of x is going to be the minus 1 over, and I'm going to change it up a little bit. It's going to be minus x minus 1 to the negative 1 power. Okay. The reason why I do that is because now I can take the derivative a little easier, right? So f prime of x is going to be 1 over 2x minus 2 times the derivative of the inside, which is 2. So this is going to be 2 here, right? And this reduces down to 1 over x minus 1. G prime of x is going to be x minus 1, negative 2. So the negative 1 drops, cancels this out, and then it's going to be negative 2 times 1. We're all done. So now the limit as x approaches 1 from the positive of the ln of 2x minus 2 over 1 over x minus 1 negative is equal to the limit as x approaches 1 from the positive of 1 over x minus 1 all over 1 over x minus 1 quantity squared. Whoa. Sometimes my computer, oh, come on. Sometimes my computer does that. It glitches at random times. So notice how we have on top and that thing on the bottom. Okay. Turns out one of these, that is on the bottom cancels out one that's on the top. So then this now reduces down to is equal to the limit as x approaches 1 from the positive of 1 over x minus, let me do it this way, 1 over x minus 1. And this now becomes limit as x approaches 1 from the positive of x minus 1. And now notice we can just go ahead and plug in our limiting factor, our 1 from the positive side, right? And this becomes 0. So here we are. Okay. All right. So here's where I'm going to try to round out stuff. This is going to be, this is going to be a large part argumentative. So just listen to the argument that's happening, right? That justifies everything for the final answer. Okay. Okay. So we wanted to find the limit of the original, right? The thing in the yellow that's in the top left corner, right? So in order to do that, right? So let me do this. So we wanted to find, we wanted to find the limit as x approaches 1 from the positive of 2x minus 2 to the negative x minus 1. That was the original limit that we wanted to find. So we had no idea what this was. So then therefore, what we did was we tried to do the limit as x approaches 1 from the positive of the ln of y, right? And we said basically this thing right here, let me do it in another color, this thing right here, we called that y, right? This was going to be our y. Okay, so we couldn't find the limit as x approaches 1 of y, so we tried to find the limit as x approaches 1 of the ln of y. Okay, that was equivalent, right, to finding the limit as x approaches 1 from the positive of the thing in the green, right? That's the ln of 2x minus 2 all over negative 1 over x minus 1. The limit of that, because of all the stuff that's on the right-hand side of the screen, right, is equivalent to the limit as x approaches 1 from the positive of x minus 1, and this is equal to 0. Okay, so from this entire line here, we have justified, right, that the limit as x approaches 1 from the positive of the ln of y, that's got to be equal to 0. Okay, so that means the outputs, listen to what this is going to be saying, right? The outputs of the ln of y, they are approaching 0, right? Think back to pre-calculus, right? If your y values for an ln are approaching 0, okay, then that means that the inputs of the values were approaching 1. So then therefore, here's the big therefore, right? This has got the big red arrow. Therefore, using all of this, right, I'm going to write it over here, right? So if the ln of y is approaching 0, if the ln of the inputs of, if the ln of the inputs is approaching 0, then that means my y values, right, must be approaching 1. Therefore, the limit as x approaches 1 from the positive of my original thing, which was my y, right, 2x minus 2 minus x minus 1, this is actually going to be equal to 1. This is our final answer. We are done after this. I know this is topsy-turvy, but it's got all the logic here. And just to sort of reinforce what I'm doing here. This is highly overly explained, okay? Because you need to listen to this explanation to make it make sense, okay? So this is what we do when we have sort of like a limit that we can't compute, right? We try to do some mathematical manipulation, use an ln in this case, to make it into that fractional form, right? And then we use L'Hopital's rule. L'Hopital's rule needs us to have it in a fractional form, okay? Using that, it makes the limit a little bit easier to compute. At the very end, we get our limit being equal to 1. Okay, and I believe that is it. I think lecture questions come after that, okay? If there's any questions with the lecture questions or the quick checks or your homeworks, please, please, please come to my office hours or my drop-in Zoom hours every day, Monday through Thursday from 3 to 6 about. Or if you guys got any questions at all, take a screenshot, send them to my email, or post them up on the discussion board, okay? Besides that, study hard, and I'll see you guys around.